Hello everyone, Dr. Miller here again. The last video I made was all about static friction, a brief overview. This is the type of friction that keeps things from slipping across one another. I'll put a link for that down below. Now making that was a lot of fun, and I instantly started thinking about what's the next video I'm going to make. And I had it in my mind, I'm going to make one about kinetic friction. Kinetic friction and static friction are related to each other, but kinetic friction is when the objects actually do begin to slip over one another. Well, that was some time ago, and since then I've had the opportunity to teach a course in the laws of thermodynamics. Very interesting stuff to me. And it got me thinking, how are kinetic friction and energy linked? Kinetic friction is a force always trying to bring an object to rest or slow it down. Friction is a force, and a force applied over some distance does work, either adding joules of energy in or removing joules out. Well, in the case of work done by kinetic friction, it's always negative, meaning it's removing energy from the object. All right, let's see if we can do a simple demonstration with the book sliding across the table to the left. All right, so let's run it back. In the beginning, my hand did work on the book, giving it, let's say, about 3 joules of kinetic energy. As soon as it comes into contact with the table, the force of friction begins to the right, slowing it down, decelerating it until its velocity is 0, giving it 0 joules of kinetic energy at the end. Now, the force of friction was to the right, let's say that's positive, and the displacement, x, was to the left in the negative direction. And if we plug that into the work equation, force times displacement, the force is positive, the displacement's negative, and so we should get a negative answer for work. Same thing applies when we reverse the direction and slide it to the right. Now, my kinetic friction force is to the left in the negative direction, but my displacement is in the positive direction now. Plugging that back in, and we still get a negative answer for work done by friction. Now, if we only think about the book, some outside force, friction, took its kinetic energy away. But energy is conserved, which means it doesn't just disappear. Energy only is transferred from one object to another, or it changes forms from one form to another. So where does this kinetic energy go? I think many people would answer this question correctly. It turns into heat, or thermal energy. On a cold day, we've all rubbed our hands together to warm them up. But we're warm to begin with. What about inanimate objects like the book? Did the book and the table actually heat up? It's hard to tell, right? Could we measure this somehow? I think it would be obvious if you were doing this experiment with an object with much, much more kinetic energy. Let's say a semi-truck going down the freeway. If the driver stopped very quickly, you could jump out of the truck, run over, feel the brake pads, and they would be hot to the touch. But can we measure the handful of joules with a small object on a table moving about 1 meter per second? More on this later. First, let's think about energy and the different types of forms that it can have. Energy can have many different forms, and we measure that in units of joules. There's kinetic energy. This is the energy of mechanical motion. Let's call that capital K. You can also have potential energy, which you may have heard of. This is stored energy, and we'll give that the symbol capital U. There's thermal energy, which we'll call energy TH. And these are the main ones that we're going to talk about, but there is also chemical energy. This is the energy that's locked inside of all the covalent and ionic bonds of some substance. And then if you zoom way down to the nucleus, there's nuclear energy. And this is the energy that holds the nucleus of every atom together. Now for this video, we're going to ignore any kinds of changes of chemical energy of the substance. And we're going to consider that all the nuclei stay together and we don't break any of those. All right. So in this scenario, we have an athlete kicking a ball through a goal. And let's consider the total energy of the ball. We have kinetic energy. We have potential energy. In this case, the most relevant kind of potential energy is gravitational potential energy stored in the gravitational field as it increases its height or its position in the field. And the ball itself is warm. Now we have expressions to calculate kinetic energy. That's 1/2 mass of the football times the speed of this football squared. And the amount of stored gravitational potential energy is going to be mass times the strength of the field on Earth times how high it is. If we consider this lowest point height equals 0. But thermal energy, we have to consider this. So if we zoom in molecularly or atomically on the atoms in the football, they are all bonded to one another. And these little green things that I've drawn represent metaphorical springs because they're all vibrating back and forth. So maybe this atom vibrates back and forth that way. And so they're moving back and forth. And so they have some amount of kinetic energy, each atom, but we'll call this micro kinetic energy. There's also a little bit of stored potential energy in this motion because as the atom gets closer to its neighbor atom, it compresses the spring, and that's stored elastic potential energy in those bonds. So there's a potential energy micro, and these are going to go into contributing to how much thermal energy is here. We need a simpler situation though. Let's think about lifting an object vertically at constant velocity, v. We're doing this at constant velocity upwards, and we've lifted it up some distance y. And if we call upward the positive direction, the tension force that is pulling on this rope that's connected to our object from this initial to this final state is doing work. Now the work done by this tension force upwards is the tension force times its displacement in the vertical direction. The tension force is in the positive direction. Its displacement is positive, and so if we multiply those two together, we should get some positive work done by tension. The total energy is K plus U plus thermal energy, and we want to know how the total energy changes from initial to final. So if I put a change in total energy, that means I need to put a change in all these individual things, and then the amount that it's going to change is going to be equal to the amount of work done on it. So work equals the change in kinetic energy. Each one of these changes is a final minus initial. So let me expand that out. and we get final kinetic energy, initial kinetic energy, final potential, initial potential, final thermal, initial thermal. And I'm going to put all the initials over here on the left. Energy. Now let's just kind of make up some arbitrary numbers and make a little bar graph here. Let's say we start with 2 boxes of joules initially. That's defined by how fast it's moving. And in the beginning, if we're looking at the picture here, we have no potential energy, so we're at 0. And there is some thermal energy. This is probably at room temperature. It's not at absolute 0. I'm going to say we're going to give it 1 box of thermal energy. And we are going to add joules, because we have positive work done by the force of tension. How much am I going to add? Let's put 3. All right, on the other side, the final kinetic energy has to be equal to the initial kinetic energy because it was constant velocity. So I still have 2 bars or 2 boxes of kinetic. I lifted it up higher, so I'm going to have more potential energy, but how much more? Let's skip that for a second and think about thermal energy. Did the box get any hotter as I went from this low point to this high point? If you did it slow enough, probably not. So that's going to be the same as it was initially, 1 box. And so the joules that I put in went into, that's how much I had initially of potential energy, but I need 3 more boxes of potential. Overall, the work done, and let's say this is the net work done, this could be the work done by all the forces, is going into gravitational potential energy. Now let's drag an object across a table at constant speed. Here's the initial state. Here's the final state displaced over some positive amount. The tension is in the positive direction also. So that means that the work done by the tension force in this case is positive. Let's say we have, again, 2 boxes of joules for initial kinetic energy. We're at the lowest height, so we have no potential energy gravitationally. And let's say we have thermal energy that is 1 box high. And we did positive work again. We put in joules. Let's say we put in 3 boxes high. Same situation as before. We didn't speed the box up or slow it down, so it must have the same amount of kinetic energy. We didn't lift it up any higher, so it has still 0 gravitational potential energy. And there's only one more place where the work that we put in could have gone. 1 box plus 3 boxes here. So we heated the object up. It has more thermal energy. And where did it get that? From the work that's being done by the tension force. Now, if we're going to be able to measure the increase in thermal energy of the book or the table as the book slides across it, we're going to need something special. We're going to need a thermal camera. This is an infrared camera, or FLIR, forward-looking infrared. And what it does is it measures the amount of infrared radiation coming from an object at all points on the object. Here's a picture I took of my cat. And the way you look at this is there's a color coding. So the orange colors are the hottest temperatures in the picture, and the blue colors are the coolest temperatures in the picture. So my cat's eyes, nose, and mouth are warmer than its ears and the rest of its body. For reference, here's a picture of my dog having a cold nose compared to the rest of its face. Okay, let's try this camera out with an object sliding across a table. So I'm about to throw at an object from the left. You can see the streaks of thermal energy left behind. Let's see that again in slow motion. Interestingly, you can see where my fingers were touching the block or the box, and the thermal energy transferred from my warm hands into the wood. Here's a couple extra throws, so you can see some different versions of that. In this example, I pull a block along the table with a string, and I have a weight on it to increase the normal force, which increases the force of kinetic friction. About right here, I start to pull it quickly, and you can see a pretty good warm streak behind the object. Let's see that again in slow motion. We tend to think of kinetic friction as a singular macroscopic force because that makes it easier to deal with. But friction between the box and the table is a conglomerate of many, many forces between quadrillions of molecules colliding with one another. Every collision transfers kinetic energy between molecules. These foam pads are an excellent representation of what's happening at the atomic level. The two surfaces resist dragging across one another. Interestingly, if you put two soda cans in between the two surfaces, this simulates what it would be like to put a lubricant in between two surfaces, the lubricant being molecules that can roll and slide past one another much easier than the two surfaces would. On the bottom of the box, you can see that it's at room temperature. There's no hot spots, and the points of contact are on the edge. And if I push down and swirl it round and round, you can see this effect very well, even on the bottom of the box. This is one of my students playing around doing this effect with his shoes on the floor. You can see the bottom of his shoe is also warmed up, but when he lifts the left foot, you can see that that is not warmed up because that foot was motionless. Using this PhET simulation from the University of Colorado at Boulder, we can visualize what's happening at the atomic level. The top surface and the bottom surface are these two books, and I can animate this and push them together and rub them. Kinetic energy transferring between all the different collisions and raise the temperature of the two surfaces. Well, I hope you learned something about kinetic friction and how it removes kinetic energy from an object. Where does this energy go? It turns it into thermal energy, heating up the object and its environment. It's time to moonwalk out of here. See you next time. Thanks for watching.